global atmospheric circulations. Now we're going to talk a little bit about some other really key circulations that have major impacts on our weather, but are also partially ocean circulations, namely ocean currents. And then we're going to talk about what's called the Walker circulation and how it relates to our good friend El Nino. So let's jump in. So first off, let's talk about this idea of ocean currents. So, contrary to popular belief, the ocean does not just remain stagnant. Now, I'm sure that this is obvious in some ways when you see waves churning up the ocean, but there's actually larger scale motions that take place in our ocean. And we call these large scale motions currents. They're gigantic bodies of water. They're almost like giant rivers of water that are constantly on the move along the ocean. And as I just said, we call these ocean currents. Now, the way that these ocean currents work, and really the usefulness or the importance of them, is that they could take a body of ocean water that has a specific heat and a specific type of matter in it, either a high salt content, what we call salinity, or a high level of nutrients, or so many other potential things, a high amount of phytoplankton or other types of life. And it takes that stuff from one location and it travels it to another location. If you've ever seen Finding Nemo, there's that scene where all those sea turtles are traveling along the EAC, dude. If you haven't seen that movie yet, go check it out. But it's basically like that. It's a large body of water that things travel along, and that it travels, and it can carry things with it. There's actually some really cool examples of this. So there are actually two different types of ocean currents. There's surface ocean currents and deep ocean currents. 99.9% of what we'll talk about in this class are specifically related to the surface ocean currents. There's one thing I'll mention about the deep ocean currents. There's one called the thermohaline conveyor. And if you've ever seen the movie The Day After Tomorrow, it's actually mentioned in that movie as part of what's called the North Atlantic Current. We'll talk about that current in depth when we talk about global climate change. But for today, we're going to stick with surface ocean currents. So here's how surface ocean currents work. Surface ocean currents are components of a larger scale circulation called an ocean gyre. And these ocean gyres are large, basically swirling circles of ocean currents. And they carry ocean water along coastlines and along the equator. These ocean gyres rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And there are actually 5 ocean gyres. There's one in the North Atlantic, one in the North Pacific, one in the South Atlantic, one in the South Pacific, and one in the Indian Ocean. And again, in the northern hemisphere, they rotate clockwise. In the southern hemisphere, they rotate counterclockwise. There's actually a reason why this happens. And it all has to do with the fact that the centers of these ocean gyres happens to be at about 30 degrees. And if you recall from our last lecture, high pressure systems also happen to be at about 30 degrees. So we'll talk about that more in a moment, but just for now, there are 5 primary ocean gyres: North Atlantic, North Pacific, South Atlantic, South Pacific, and the Indian Ocean Gyre, also referred to as the South Indian Ocean Gyre. Now, if we took each one of these gyres, so here they are. Here are our 5 beautiful gyres. This is North America right here. North America, South America. Then over here is the Atlantic Ocean. This is the North Atlantic Gyre, the South Atlantic Gyre. Over here is Western Europe. Over here is Asia. Down here is Australia. One thing that a lot of students love to do is they love to take this Indian current and put it beneath Australia. Nope, the Indian Ocean current is the Indian Ocean Gyre is entirely in the Indian Ocean. With this said, each of these gyres has a different component to it. And I'm going to talk about each one of these components right now. So here are the components. The components are called the eastern boundary current, the western boundary current, and the equatorial current. So eastern boundary current, western boundary current, and equatorial current. Now for us to understand what kind of a current we here in California experience, I have to ask an important question. Are we on the west or the east? Now, if you lived in California for any amount of time, you've probably heard that we are West Coast. We're West Coast for life, or West Side, or just West Coast. West Coast is the best coast. We're often referred to as the West Coast. Now, that is true from a continental perspective. If you look at a giant map of the United States, north is on the top, south is on the bottom, west is on the left. And we are on the left end of the United States. We are on the West Coast. However, if you were to then swap that map out for a map of the entire Pacific Ocean basin, what you would actually find out is we are on the eastern end of the Pacific. So from an oceanic perspective, we are on the eastern end of the Pacific Ocean. A good way to understand this is go grab a map of the Pacific Ocean. Make sure it's a map that has the whole Pacific Ocean on it, not one that cuts off at the international date line. Many maps do that. Look for one of the entire Pacific Ocean. Put your finger right in the middle of it, and then travel to the east. Again, if north is at the top, east should be to the right. As you travel to the east, you'll notice that you quickly run into North and South America. On the other hand, if you travel to the west, you end up in Asia. So yes, even though we are on the west coast of the United States, we are on the eastern Pacific. That's going to become very important in a moment. So yeah, we're here in the eastern Pacific. So here's a map that I pulled up of the Pacific Ocean. And this is often referred to as the Pacific Ocean Basin because it's basically like a giant bowl. It's basically like a giant bowl. So there's the Pacific Ocean Basin. Hawaii is right in the middle, a little bit further to the east, but it's good enough. If we started in Hawaii and traveled east, we would end up in North America. If we started in Hawaii and traveled west, we'd end up in Asia. So yes, even though we're on the west coast of the United States, from an oceanic perspective, we are in the eastern Pacific. Now with that said, let's talk about the different components of an ocean gyre. Going back to this map, let's talk about each of the components. So as I said, there are three components I really want you to know about. The first component is called the western boundary current, on the western end of the ocean basin. This is the region on the west end of oceans. So an area like East Asia is on the western end of the Pacific Ocean, or Eastern Australia is on the western end of the Pacific Ocean. Along these areas, because ocean gyres are traveling clockwise in the northern hemisphere, there, warm water from the equator is traveling up towards the poles. We call this poleward movement. Think about if you were traveling towards your door, you would be traveling doorward. In this case, water is traveling poleward. It is heading towards the poles. A good example of a western boundary current is called the Gulf Stream. The Gulf Stream is an ocean current in the western Atlantic right along the eastern seaboard of the United States, where warm water travels up that current towards the poles. And actually, if you've ever been to the East Coast in the summertime and you go out to the beach, oftentimes the water feels really warm. Some people even say it feels like bath water. It's because of the Gulf Stream. It's because of this warm western boundary current. On the other hand, On the eastern basin, so now we're on the eastern end of the ocean gyre, we are a part of what's called an eastern boundary current. Here, cold water from the poles is traveled equatorward. It's traveled from the poles down to the equator. And since the area near the poles is usually very cold, the water near the poles is very cold. This is where we as Californians are located. We are located right next to a cold eastern boundary current. And that's actually what gives us our cold water. If you've ever gone swimming in the beaches off our coastline, so Santa Cruz or Mavericks or Half Moon Bay or Ocean Beach or anywhere along our coastline, even down to Southern California, it's relatively cold, right? It's relatively cold. Well, that's because we are along a cold eastern boundary current. We're on the eastern end of the Pacific Ocean. We are next to a cold eastern boundary current. And then finally, down near the equator, a third type of current called the equatorial current exists. And along the equatorial current, water is carried from east to west. From east to west. So if you were to look at a map, here's a map of all of the ocean basins and all the currents. Examples of western boundary currents include the Kuroshio Current in the western Pacific, the Gulf Stream over here in the western Atlantic, and down here in the West Indian Ocean. These are western boundary currents. Warm water from the equator travels up and along the coastline. On the other hand, on the eastern end of the oceans, we have these eastern boundary currents that carry colder water from closer to the poles down along the coastline towards the equator. Again, this is why our water here in California is so cold. And then finally, equatorial currents. Equatorial currents carry water from east to west. Now, what actually drives these ocean gyres? Well, the answer is wind. It's all about wind. And what actually happens is we have those areas of semi-permanent high-pressure systems over our ocean basins. We have one over the Pacific. This is called the Pacific High. We have one over the Atlantic. This is called the Bermuda High. Then we have a series of high pressures over the southern oceans, the southern Pacific, southern Atlantic, and over the southern Indian Ocean. Here in the northern hemisphere, these oceans, or these high pressure systems, rotate clockwise. That creates clockwise rotation, which then creates a clockwise turning gyre. The winds blow over the ocean water, pushing it in the same direction. The same thing happens here. Meanwhile, in the southern hemisphere, the winds rotate counterclockwise around high pressure. And that's because the Coriolis force reverses direction in the southern hemisphere. So we have counterclockwise winds blowing around high pressure here, here, and here. And so those ocean gyres rotate counterclockwise in the southern hemisphere. Now, there's more to it than just this. If you wanted to learn more about what actually drives these ocean currents, there's a process called Ekman transport that occurs that creates this basic spiraling of ocean movement from the surface down to a few meters below the ocean, actually a little bit even deeper than that. That's a little beyond the scope of this class, but if you're ever interested in learning it, we here at Deanne's offer a really cool oceanography class online as well. And I know that the instructor there goes way more into depth on it. But for us right now, we just need to know wind is what drives these ocean currents. Now, with that said, just a review from our previous lecture, we talked a little bit about different types of wind. And there were three main types of wind, or there are three main bodies of wind that I really talked about, and I want you to know about them again. They are the trade winds, the mid-latitude westerlies, and the polar easterlies. The trade winds start at the equator and move up to 30 degrees north and down to 30 degrees south. So between the equator and 30 degrees, you have what are called the trade winds. These winds blow primarily from east to west, and so they carry water with them from east to west. On the other hand, between 30 and 60, both north and south, a large wind blows from west to east, and we call that the mid-latitude westerlies. And then finally, between 60 and 90, that would be the polar easterlies are present, and they blow from east to west again. And so they look kind of like this. So you have winds blowing from east to west near the equator, winds blowing from west to east between 30 and 60, and then between 60 and 90 from east to west again. Now, the most important of these is really the trade winds, but I want you to know about the westerlies as well. And so we ultimately get gyres that look just like this. So, and you can see this here. Here's our North Atlantic gyre. Here's our South Atlantic gyre. Our South Indian gyre. Our North Pacific gyre. Starts on this side, goes over to this side. This is one of those maps that cuts off at the international date line. And then our South Pacific gyre. But it's actually really cool to think about how this whole three-celled model that we talked about in the last lecture has major implications on ocean circulation. And believe it or not, these major implications on ocean circulation then have major implications on climate. So one of the things I love to tell people about California is California has some of the greatest weather in the world. Think about this. If you live here in Silicon Valley, like I do, if you live here near De Anza, this summer, we may have a day or two where temperatures go above 100. Very rarely. We also will have a handful of days where temperatures jump into the 90s. But for the most part, we don't get much warmer than the 80s. And even when we do, it's not very humid. If you've ever been to the East Coast during the summertime, it's the exact opposite. 85, 90, 95 degrees, 90% humidity. It's miserable. Well, we have ocean currents to thank for our awesome weather. And here's why. Here along the eastern Pacific, we have that cold eastern boundary current. Meanwhile, over on the east coast of the United States, they're next to the western Atlantic, they have a warm western boundary current. That's the Gulf Stream. And as a result, there's a lot of heat and a lot of moisture carried up along that current. So as a result, they get a lot of hot, moist weather. Ends up being very miserable for them. Meanwhile, here on the West Coast, we get nice, cool, calm, relatively dry weather in the summertime. So granted, if you're like me, I don't like it when it gets into the 80s or 90s, but it's still way better. So how is this influenced by ocean currents? Well, here on the West Coast, we have a cold ocean current. That does a good job of keeping our temperatures from getting too hot. But the other benefit is that there's not a whole lot of heat in that water, hence there's not a whole lot of evaporation. As a result, the air doesn't get very moist. And so we have relatively cool weather, and it's relatively dry. Meanwhile, our friends on the east coast of the United States, next to the Gulf Stream, it's warm, it's muggy, and we'll actually talk about this in a few modules, but that heat and that moisture add up together to create thunderstorms as well. So they have all that heat, all that humidity, all kinds of thunderstorms. Meanwhile here, Nice, cool, dry weather. Another good example of this, and I think I covered this a few weeks ago, but it's worth re-mentioning, is there are two cities in South America. The first city is Arica. It's on the coast. It's at a very similar latitude to Rio de Janeiro, but it's next to the cold Peru Current. And if you actually take a look, as a result, its temperature on average is relatively low compared to Rio de Janeiro. Temperatures seldomly get out of the 60s, maybe a little bit in their winter months, but they seldomly get out of the 60s. You don't get those 70, 80, 90 degree temperatures that you see in a lot of other places. And another interesting thing is Arica is a part of the Atacama Desert. It's actually one of the driest locations in the world. On the other hand, Rio de Janeiro, on the other side of the continent, next to a warm western boundary current, is substantially warmer. Their temperatures regularly get above 80, and they regularly get a lot of moisture and hence a lot of wet weather. Very humid, a lot of tropical diseases can happen. It's a lot warmer, a lot muggier there. And it all has to do, again, both cities, similar elevations, similar latitude, so right on the coastline, but the only difference is this ocean current. Arica's next to a cold ocean current, Brazil's next to a warm ocean current. Now with this said, these ocean currents are semi-permanent, but there can be some variation. We're going to talk about that in the next part of this lecture on El Niño and La Niña. Until then, thank you for watching.